Before we do today's notes, I wanted to share with you my work environment. So you can see I got a nice view of my neighbor's property. I got all my plants ready for spring planting, growing up nice. I got a pile of lab books I got to grade. And then I got a great view of the outside where every once in a while I get a nice bird, bluebirds, cardinals, and things landing right outside my window. Anyway, here are today's notes. Good morning. Today we want to welcome you aboard the Axiom for day 3. Today we're going to look at some more things dealing with the magic of moving charges. We want to remind you that if the particle is not moving, the charge will not feel a magnetic force. That is an extremely important idea. Stationary charges do not feel magnetic forces. Moving charges do. This was the formula to figure out the strength of the magnetic force. We saw that we had to represent vectors in 3 dimensions, and we learned how to use our left hand to find the direction of forces when the charges are negative, and our right hand when the charges are positive. We saw something very important, and that is when the particle enters into a magnetic field and the force deflects that particle, the direction it travels is constantly changing, so we constantly have to change the direction of our thumb and fingers and palm, and it creates a circular path. We use that for 2 different things. One is we use it to contain antimatter. As you know, antimatter cannot exist in our universe. As soon as antimatter touches regular matter, they both annihilate. So we get our antimatter and we put it in a magnetic field and it goes in circles. As long as the walls of the container are outside the circumference of that circle, this particle will not come in contact with the walls. If we keep the inside as a pure vacuum, this antimatter will not contact regular matter, and we can contain it until we want to use it for studying or for producing energy. We saw the formulas that let us figure out how big the circle would be. We find the force magnetism, we find the acceleration, and finally we find the size of the circle. Then we learned about velocity selectors. You don't know quite why these are important, but we will see that today. We saw that they came from Thomson's electron beams. We saw that when there was only an electric field, the beam hit the top plate. We saw that by having a magnetic field, we could lower the path that the electron follows. We saw that if we had the magnetic field just the right strength, the beam would travel in a perfectly straight line. If the particle was moving any faster, it would hit this bottom plate. If it's moving any slower, it hits the top plate. So the important thing is that only one velocity is able to get out of this velocity selector. The reason that's important is we can fire particles, they can go through our velocity selector, and now we know the exact velocity of the particles when they come out. And then what we do is we have them go into a second magnetic field. And in that second magnetic field, there is no other force other than magnetism. So these particles will travel in a perfect circle. They will then hit a screen and cause that screen to light up, or they will hit a detector which will measure the exact spot where they hit. So for instance, if we send ionized chlorine through this velocity selector, we will find that on that screen are 2 separate dots at 2 different radii, 2 different diameters based on where they entered into this field. And based on those 2 different diameters, we can find that there are actually 2 different masses for these particles. This lets us know that there were 2 different ions of chlorine. This is how we know that even though we have the same element, we have different masses for it because of the fact that they hit in 2 different locations. You saw this if you were in AP Chemistry. Miss Dare was teaching you about this, not that you understood all the physics behind it, but she showed you that when they look at this and they fire chlorine through their mass spectrometer, that they get two peaks, one around 35 AMU and one around 37 AMU. They find that many more particles are hitting at 35 compared to 37. So not only can they figure out the mass of the different isotopes, they could figure out the relative abundance for those isotopes in nature. So a very important device. Again, it's called the mass spectrometer. You can buy a mass spectrometer if you have an extra $11,000 laying around. You can get them at Amazon if they still have them. And these mass spectrometers are used in research labs for trying to figure out the mass of molecules, of new things that we have never seen before. All we need to do is send them through the mass spectrometer and we can figure out what mass they have, and that helps us figure out what they are composed of. Okay, in addition to the mass spectrometer, the other thing I'd like you to learn today is that the charges don't have to be loose to feel a force. So in this case, we're going to run electricity through a wire, and we're going to put the wire in a magnetic field. And when we do that, you'll notice that the wire gets shot right out of the magnetic field. Again, it's the same force we've been looking at. Moving charges in a magnetic field feel a force. It's just that this time the charges are not loose, but they are confined to within a wire. We can see it here also. We have our north and south pole. We have our wire carrying the current. And you can see the wire getting shot out of the magnetic field when I run electricity through that wire. This is the basis for a thing called the railgun, a very cool little thing. And what you do is you get two metal rails, almost like train tracks. You hook it up to some sort of power source, and then you drop a piece of metal on it. When you drop a piece of metal on it, you're going to complete the circuit. Electricity is going to flow through this rail. That rail is then placed in a magnetic field, and that rail will then feel a force that's going to shoot it along these rails. It will accelerate the whole time it's moving, and it will leave these rails at potentially very high speeds. In fact, these are thought to be the fastest type of projectiles that we can create. In this case, it's not going to be going that fast because we have a moderate voltage, but these can reach incredibly high speeds. When you're figuring this out, instead of using the formula force magnetism equals QVB, we now use the formula force magnetism equals BIL. B is still the strength of the field. The I is the current, which is how much charge is flowing through our thing and how fast it's flowing. And L is the length. Now, when you do the length, you only do the part that is actually carrying current through the magnetic field. So it would only be this part of the rail. And again, this is known as a rail gun. And depending on what direction you run the current, you can either have the rail shoot to the right or shoot to the left. Here it is in real life. I wish I could show you this in person, but this will have to do. So I have this one hooked up to 12 volts. I drop it onto the rails, and you can see how it's shot to the right. Again, if I reverse the direction of the electricity, or I reverse the direction of the magnetic field, this thing would have shot in the other direction.